right, so this lesson is on double replacement reactions. And our goals kind of for the end of this lesson are 1, to be able to predict the products for this type of reaction. 2, to be able to classify those products as either soluble, able to dissolve, or insoluble, which does not dissolve. And then identify the formation of a precipitate. And so typically, if we had more time in the semester, what we normally do for Unit 8 is we take a more in-depth look at each type of chemical reaction, and they're actually kind of listed on the back of your blue sheet. There's synthesis, decomposition, single replacement, double replacement, and combustion. And what we typically do is go through and talk about like how you can predict what products you would make for each reaction before you ever go in the lab and do the reaction. And it's amazing because what people have done is they've watched these reactions, lots and lots and lots of them, and they've kind of come up with some patterns or rules that the reactions tend to follow, every time. So for example, for synthesis reactions, the elements tend to start by themselves and come together into one product. For decomposition, the compound is what you begin with, and it breaks down into 2 other simpler substances. For single replacement, you have a single element swapping out with an element in a compound. And then for the main focus of today's lesson, double replacement, you have 2 compounds that are each consisting of ions, and those ions are going to swap places. So if you notice, kind of from reactants to products, B and D have swapped places so that you generate 2 brand new compounds, AD and CV. And so we decided that kind of out of these different types of reactions, double replacement is going to be the most likely that you'll see again if you go on to take chemistry in college. And so we decided we'd take a day and kind of focus in on that specific type. So let's see if we can tackle our first learning target, which is write and predict the products for the following double replacement reactions. And so I'm going to see if I can split my screen kind of right quick. And if you have it available in the back of your lab manual, you'll need your blue reference sheet and your charge chart. That way you can see kind of the different ions while we do this. So let me pull that up for us over here. There we go. All right, and so I've got it condensed on one page over here where we've got our ions and then our polyatomics all right there. Okay, great. All right, so example 1, it gives us silver nitrate and potassium phosphate. So the first step we want to take is actually generating those compounds. So we have the element silver, which is a positive one. We have our polyatomic ion, nitrate, which is a NO3 with a -1 charge. So if we're putting those together, it just looks like AgNO3. Then we write our next compound. Potassium is the symbol K. It has a +1 charge. Phosphate is a polyatomic ion with the symbol PO4 with a 3- charge. Therefore, it's going to take 3 potassiums to match with the phosphate. So those are our 2 reactants. Now, what we're going to do is because they're ions, we can swap places. We can either swap the 2 positive ions, or we can swap the negative ions. To be consistent, what we're going to do for our purposes are just swap the 2 cations. So what this means is silver and potassium are going to swap places. And so now potassium will come over and be with nitrate, and silver will come over and be with phosphate. So from this kind of first compound, nitrate has stayed in his place, but now potassium has come over to be with him. They're both in a 1-to-1 charge ratio, so that first new product will be KNO3. Then for our second product, phosphate has stayed in place, and now silver has come over to be with him. Since silver is a +1 charge, we need 3 silvers to match up with the phosphate. And so what you're noticing is that each new time we build a compound, whether it be a reactant or a product, we need to think about balancing our charges. Okay, then just like any other reaction, at the end you would go back and kind of balance the equation overall. So I have 3 silvers on the right, so I'll put a coefficient of 3 on the left. That then gives me 3 nitrates. I'll put a 3 on the right so I can have 3 nitrates, and that should take care of my 3 potassiums as well. All right, and so there you go. That's writing and balancing the products for a double replacement reaction. Let's go ahead and try example 2. Okay, so here we have calcium hydroxide plus phosphoric acid. So if we look on our charge chart, calcium has a 2+ charge. Hydroxide is a polyatomic ion with a 1- charge. Then phosphoric acid, if we remember from our naming unit, phosphoric is referring us to the atom, or the polyatomic ion, phosphate, which is PO4 3-. And since it's an acid, it should have hydrogen at the front. So if we balance those out, it should take 2 hydroxides to match with the calcium and 3 hydrogens to match with the phosphate. Now, let's go ahead and swap our ions. So calcium will be swapping with hydrogen. And coming over here. All right. So now what remains behind from that first compound is OH is still in the same place, but now it's going to be paired with H. From the second compound, the PO4 3- is still in place, but now it's going to be paired with calcium 2+. Now what's neat is here for the H and OH, we see that we just need one of each. And what that makes when you combine a hydrogen ion with hydroxide is that actually gives you water. So pretty cool there. And then for our other reaction, 2 doesn't go into 3 evenly, so we need to think about shooting for 6. So if I take 3 calciums and 2 phosphates, that would balance out with a +6, -6 charge. Then I go back and balance my reaction, just like in previous units. So let me get a pen in there. All right, so I've got 3 calciums on the right, so I'll put a 3 on the left. I have 1 phosphate on the left, but 2 on the right, so I'll put a 2 there. Then now let me check on my hydrogens and oxygens here. I have 6 hydrogens in calcium hydroxide, 6 in my acid, so it's a total of 12. So I need to put a 6 in front of my water to get to 12 hydrogens, and that should fix my oxygens. 6 oxygens in water, 3 times 2, 6 oxygens here as well. All right, now last example here, let's do it just one more time. So here we have iron 2 sulfide, and remember that Roman numeral 2 tells us the charge of iron. Sulfide is sulfur, so that'll have a -2 charge. And then hydrochloric acid, hydro means no O, so you should have a hydrogen being paired with chlorine. Hydrogen is +1, chlorine is -1. So let's put those things together. They already balance in a 1-to-1 ratio, so our products are FeS plus HCl. Now we're ready to do our swap. We're going to swap out iron and hydrogen. All right. So in our first compound, sulfur hasn't gone anywhere, but it's now going to be paired with hydrogen. In our second compound, chlorine hasn't gone anywhere, but it's now going to be paired with iron. I'm going to close out that for a second so we can have a little more space now. All right. There we go. So now let's build those 2 new compounds. I'll need 2 hydrogens to match with my sulfur. And then my iron, since it's a 2+, I'll need 2 chlorines to balance out that charge. Then you go back and balance at the very end. So I have 1 iron on each side, so that looks good to go so far. I have 1 sulfur on each side. I have 2 chlorines on the right, so I'll need to put a 2 on the left, and I think that takes care of our hydrogens as well. So now that reaction is also balanced. Okay, so there you go. Now, kind of in this, that's just the basics of how to write the products. You might be wondering, well, how do these ions actually, swap? What does that look like? And so I'm going to take you to a little slideshow right quick to see if I can give you a little insight as to how that works. So when you have a double replacement reaction, what happens is the compounds are typically going to be dissolved in water before they can react. Now, if you'll notice, as they dissolve, those ionic compounds break apart into different ions. Now, if they're all in the same container, those ions can then kind of react with ions from one of the original compounds. So now, for example, we kind of see sodium and nitrate getting close and silver and chlorine getting close. So let's kind of reverse there. So here's our original compounds. They're being dissolved in water and can now move around freely and interact with other ions. Now notice right quick what happens to the silver and the chlorine as they get close together. It seems as if they bonded and then they sink to the bottom. So what you call this, if when you put all those ions together in the same container, if some of them bond and kind of fall down to the bottom, they're what's called a precipitate, and they have a solid state. Now, you may have heard, like kind of in weather, that rain is sometimes called precipitation because it kind of falls out of the sky. And it's kind of the same thing here. A precipitate kind of falls out of the solution. And so we can kind of replicate this just on a larger scale if we had more of the compounds. But again, the same thing happens. The silver and chlorine seem to bond and kind of form a precipitate at the bottom. Now you'll notice that the sodium and the nitrate, they continue to kind of float around as ions. While we call the silver chloride a precipitate, what we say about the ions that remain dissolved is we call them aqueous because they've been dissolved in water and they stay that way. Okay. Now, what this looks like, kind of if we were to see it in the lab, is it looks to be kind of very cloudy. And I think you saw this when you did the lab on your chemical reactions. But right quick, I'm going to show you kind of a famous precipitation reaction that's called golden rain. And so they're going to start with some lead nitrate. You'll notice it's aqueous, it's a liquid. Then they're going to add in potassium iodide, and we should see, there we go, a bright yellow precipitate. All right. So you're taking two liquids and generating a solid, and it makes the container or the solution very cloudy. Now, if we were to let this just sit undisturbed for a while, what would happen is the solid would all kind of collect in the bottom of the container. And so the idea is, though, if these ions don't react to form a precipitate, then technically no new substance has been made, all right? So for a double replacement reaction to actually occur, you must have a precipitate formed. Otherwise, your ions are just dissolved and floating around and nothing new, has happened. And so we may wonder, how can I tell which product will be the precipitate? So fortunately for us, kind of through different scientists observing just lots of these double replacement reactions, they've come up with a set of guidelines called solubility rules that can help us predict which product, if any, will precipitate out. And so this should correspond with your second page of notes. Now, the way you read the solubility rules is as follows. If it tells you that a compound is soluble, that means it dissolves in water. And we're going to use the state symbol AQ to stand for aqueous. If it says insoluble, that means it does not dissolve in water and it precipitates. The symbol for that will be an S for solid. Okay. Now, what you'll notice is consistent on all these reactions is the starting compounds always begin as aqueous. Then what we're trying to see is when those ions are dissolved, will they react to form something new? Okay, so let's do just a few quick practices on using the solubility rules. And again, this is the bottom of your blue sheet. So the easiest way to kind of navigate the rules is to start by looking at the anion. Then check the cation to see if there are any exceptions. The anion is always going to be located on the second half of the molecule. So for example 1, when I have silver chloride, chloride would be the anion, and nitrate would be another anion. So what I do is I go to my solubility rules and I search for the word chloride. Here I happen to find it in Rule 3. And so what it does is it says all chlorides are soluble. Okay, so in general, chlorides tend to dissolve. But now we need to check the exception. So it says except lead, mercury 1, and silver. Okay. So if we look, what atom do we have in the front? We have silver. So if it matches one of the exceptions, that means it will go from being soluble to insoluble. All right. So the normal rule was being soluble or staying dissolved, but the exception is to be a precipitate. So silver chloride would be the precipitate. We'll put in an S, or sometimes you'll see people label it PPT for precipitate. So now let's check our other product, silver nitrate. So let's search our rules for nitrate. All right, so keep searching. It's on Rule 2, and it says all nitrates are soluble, no exceptions. So that means that Na and NO3 will stay dissolved and they'll be aqueous. We did have a precipitate, so yes, this reaction will occur. All right, let's try example 2. So again, let's go ahead and pick out our anions, and we'll start with nitrate. Now we already know from Rule 2 that all nitrates are soluble. So it should have a symbol of AQ for aqueous. Then let's look at the next compound, which has sulfur as an anion. So let's search our rules for sulfide. All right, and that comes into play on Rule 6. And it says all sulfides are insoluble except group 1 and group 2. So in general, they're insoluble. Now what it means by group 1 and group 2 is the elements on the periodic table. So the first column is group 1 and the second column is group 2. So let's check our exception. We have silver, which is located in the transition metals and not in group 1 or 2. So that means the rule stands. Our sulfide is insoluble. It will form a solid precipitate. So yes, this reaction will occur because we've made something brand new. All right, just a few more examples. Hang in there. All right, example 3. So let's navigate with our anions. This time, our first anion is sulfate. That happens to be in Rule 7. So it says all sulfates are soluble except group 2, lead, mercury 1, and silver. So aluminum is all the way in group 13, so it doesn't meet one of those exceptions. So the general rule will hold that it's soluble, so we'll put in the symbol aqueous. Then let's look at our next part, barium chloride. So we have chloride, which is in Rule 3, and it says all chlorides are soluble except lead, mercury 1, and silver. All right, so in this case, we don't have lead, we don't have mercury 1, and we don't have silver. We have barium. So that means the general rule will hold and it will remain soluble or aqueous. All right. So if both products end up being aqueous, that means that technically no reaction has occurred. So we'll mark through the arrow and we'll put NR for no reaction. Because what's happened is those ions are just all floating around, but none of them have reacted to form something brand new. So if you don't form precipitate, it's NR, no reaction. All right, last 2. And feel free on these if you want to pause and kind of try these by yourself and then check them with the rest of the video. I think that'd be a great idea. All right, so now we've got kind of a new anion. We've got carbonate. So let's see if we can find him. He's in Rule 5. And it says, in general, the carbonates are insoluble except those of ammonium in group 1. So if we look on our periodic table, Barium is in group 2 instead of group 1, so it looks like the general rule will hold that carbonates are insoluble. That means they will form a solid precipitate. Then let's check our next part, our chlorine. We've done that one several times now, which is rule 3. It says, in general, all chlorides are soluble except lead, mercury 1, and silver. We have sodium, so we're good to go there. It will follow the general rule and stay insoluble or aqueous. We did have a precipitate, so we did form something new and had a chemical reaction. All right, last example, example 5. So this time we have sodium iodide. So we want to look for iodine there. That's on rule 3 as well. So it says all iodides are soluble except lead, mercury 1, and silver. We don't have an exception, so it will be soluble with AQ. Then our second compound is ammonium as the cation, and then sulfate as the anion. And so it says, in general, all sulfates are soluble except group 2, lead, mercury 1, and silver. So here we don't have an exception, which means it will follow the general rule and stay soluble, which will represent with AQ for aqueous. We did not form a precipitate, which means that we technically didn't have a chemical reaction. So we'll mark through the arrow and put NR for no reaction. All right. Well, guys, that was kind of a lot to throw at you, but I'm super proud of you for hanging in there. So now what you can do is go and try, I think, the 5 practice problems on the homework, and then you can call it a day. Thanks so much.